Hello, good evening. Can you hear me?
Yes, sir.
Okay, yeah, we'll get started in a couple of minutes. Okay.
Okay, sir. Sir, I have two doubts in previous assignment questions, sir.
Okay. Shall we discuss at the end of the lecture?
Okay, okay, sir.
Okay, yeah. Okay, yeah, let's get started. So, good evening, all. So, welcome to session 8 of this course for this problem solving session for the course optimization methods. So, in this session, we will be looking into some problems and some concepts that have been taught in the previous week, and we'll see also solve some problems. So before that, I will just brush up the concepts that have been taught, including how to solve a problem with genetic algorithm. Then we will see what is real coded GA, and on some of the methods like new methods for like what we can do for crossover and mutation. We'll see through the process, and then we'll solve some hands-on problems. Okay, so before proceeding, like, I will just brush up the concepts that have been taught. So I am taking some time for that. So first, there is something in last class. If you remember, we have discussed about selection procedure and crossover mutation. So there is one more thing that comes in between selection and crossover, and that thing is called elitism. So elitism means what? It's like a preservation of best solutions of the population pool. So when we are first initially doing the selection, there will be some solutions that will be very good solutions. So before going into crossover and mutation, we will want to keep those solutions in the solution pool for even for the further generations. So this process is called elitism. So elitism is defined as a percentage or number. Like we'll suppose keep one like 0.01 or 0.02 percentage. So what it means that like initially the 2% of the solution will be kept as separately, so it will be preserved for all the generations. So this is called elitism, and it's very important to preserve good solutions when you are proceeding before crossover and mutation. Okay, because in mutation and crossover sometimes what happens, like if you're taking all the solutions and not preserving this, after mutation this we might lose some of the best solutions. So that is why we need to preserve some of these solutions. This is called elitism. So then we discussed about like what is termination criteria, like what is the maximum like this were defined by the maximum generation number of generations we want, or the solution, or we'll say that generation, suppose after a specific number of iterations the solution is not improving more. So we'll set that as a termination criteria. Okay. So these are the uh, uh, what what you call the terminologies related to genetic algorithm. Population is defined as set of solutions. Individual is called a solution. The fitness is defined as the quality of the solution. The chromosome is the encoding of the solution, and the gene is the part of the encoding of the solution. So we have discussed that it is whole string with different bits with numbers 1010 like 11. So it is a, if it is binary coded, if this is, so it's a binary coded. So this binary coded string is a chromosome, and its bit is called the gene. So, so this is a sample problem. How we will do that? How we will solve a problem using a genetic algorithm. So suppose our sample space is 4. This was discussed in class. Just I will quickly go through it. Our sample space is 4, so we initialize the first set of populations, and this is generated randomly. And how we will generate? We can generate using a coin toss, or we can generate using like dice or like that. So if we generate a coin toss, suppose if it comes head, we'll keep it as 1. If it comes tail, we'll keep it as 0. So we'll do 6 coin tosses, and based on that, we'll keep 0 or 1. So this is how we like define a random string, and we have taken 4 random strings. Now we'll get the decoded value of the string. The second step is getting the decoding the value of the string. So how do we decode it? I taught you last class. We have to multiply each number 0 1 by the corresponding power of 2. So 0 into 2 to the power 0, 1 into 2 to the power 1, 1 into 2 square, 1 into 2 cube, 0 into 2 to the power 4, and last 1 into 2 to the power 5. And then we'll add up all the numbers, and then we'll whatever you get is called a decoded value. Now we have the decoded value. From the decoded value, we have to find the x value, that is for our problem. We'll be given a problem. Suppose I think in this problem it is a I think sine problem, sine pi x. I think sine pi x. So it is sine pi x. We have taken the value of x from 0 to 1. So this is the range of solution 0 to 1. So this part x min x max minus x min divided by 2 to the power li minus 1. This is called the precision of the solution, and precision is denoted as pi. Pi is equals to x max minus x in divided by 2 to the power li minus 1. So based on the precision, we'll fix the length of the chromosome. So in this case, our length of the chromosome is 6. We have already defined that as 6. So it will be 2 to the power 6. Why 6? There are 6 bits in the chromosome. That is why we are taking length as 6. 2 to the power 6 minus 1. What is x max? X max is 1 and x min is 0. Since our solution is varying from 0 to 1. So this is our precision. It is equal to 0.0 0.01, right? Yeah, 0.01. I think one more it will come. I think 0 something 0.01 or something like that. Yeah. So we will always keep a precision based on our requirement. If we have one more number of iterations, or we want like more precise solutions, we'll keep a very high precision like 0.001 or 0.0001 like that. But as we increase the precision, the complication of the problem will also increase. The computation time will also increase. So we have to fix that number very carefully. So once we get the precision, after that we'll multiply it by the decoded value, and then we will add it to the x minimum. So after adding it, after doing this procedure, we'll finally get this x value. So these x values are 0.58, 0.19, 0.92, 0.73. We have got this. Now we have what we
Here
define.
x minimum is 0, sir. Here x minimum you have to take is 0.
Yeah, yeah.
Okay.
Because I told you in the question it is defined as the x
Okay.
is ranging from 0 to 1. So minimum x it can take is 0.
Okay.
And our fitness function is this sine f of x is equals to sine pi x. So we have to maximize this function. So this is our fitness function. Okay. So we'll find so we have x values. So we'll substitute x in this sine pi x formula, and we'll get these values 0.96, 0.56. For each of the values of x, we'll get this f of x value. It is fitness function. Now, now this is a maximization problem. Since it is a maximization problem, so our fitness function will be equal. Our function value is will be equal to the fitness function. Okay, but I told you in last class, if we have a minimization problem, then our fitness function will be defined as 1 by fx, because we always want to do the maximization in case of GA, since genetic algorithm designed in that method. And this is a prime difference between genetic algorithm and classical optimization. In classical optimization, what we do, we always try to get the converter problem to a minimization problem, because that is we want to get a convex function. But in case of genetic algorithm, we always want to get a maximization problem. So even if there is a minimization problem, we'll try to convert it to a maximization problem. So clear? So after this, we get the fitness function values. So no change in the function as it is a maximization function. Now relative fitness. Relative fitness is what? It will be a fitness divided by the this is divided by the sum of the fitness. RF equals to fitness divided by sum of F. Okay, we'll get a relative fitness. This is for each of the chromosome. We got the relative fitness. Now we want the expected count. So what is the expected count? Expected count is the relative fitness multiplied by the total number of chromosomes. That is the population size. And population size is 4. So here it will be RF into 4. Okay. So if your population size is 5 or 6, we will multiply it by the corresponding population size. From that, we will get the expected count, and we'll convert the expected count to actual count by taking the round off. Okay, so it got the actual count. Like after the first round of selection, we will have the two solutions of the first one solution of the second one, no solution of the third one, and one solution of the fourth one. So you can see in the population size is preserved. Initially we had 4, now also we will have 4. But there are 2 copies of the best solution. It is the first solution is the best solution here. So there will be 2 copies of that solution. Okay. So this is we after a first round of selection we'll get this actual count, the 2 solutions of first, one of second, and one of fourth. And there will be no solution of the third one because it is a bad solution. Now what we do, like we want to see, like select C for more search areas, that is going to do a local search. For that we do a crossover, and from crossover we want to get a new population. So how do we do the crossover? We'll take 1 and 2. I think here we are taking 1 and 2 only. Yeah, 1 and 2, and then we are taking 1 and 4, right? Yeah, we are excluding, this is the first solution and a second solution here, and this is the first solution and the last solution, it is fourth solution here. So these two will be crossover and these two will be done crossover. So we already have decoded value of its 37, 12, 37 and 46. Okay, corresponding decoded value also have the corresponding x values. Now we have to decide a crossover site. Where do you want to do a crossover? So we can select it randomly. So randomly we select crossover site. For this, let us say our crossover site is the third site that is given here, and for this one the crossover site is okay. So after doing the crossover, we'll get the new strings from the first two and 2 new strings from the second two. So now we will do the same procedure. We'll get the decoded value, then we'll get the x value, and then fitness function and a fitness function value. So we see that there is no there is not much change in the fitness function, as we have already in the best solution in the first one. For the other solutions also there is not much change. The fitness functions are not much changing. Okay, but it is we are slightly going to a higher fitness. From 0.96 we are going to 0.97. Okay, so this was after crossover. We did a local search, and now we will do something called mutation. In mutation, we discussed in last class that we change one bit from 0 to 1 or 1 to 0, and then we see like we'll see search for other regions in the population where we can have a optimal solution. So we do that for first one. We change the third bit. For the second one, we change the this one last bit. Third one again fourth bit, and the fourth one we say change the fourth bit. And see, for the population that we do mutation, this population will come from this one. Okay, not the initial population. Okay, we shouldn't take the initial population for mutation. The population after crossover, that will be input for the mutation, because we are doing this in a sequential way, sequential manner. So after changing, we have the decoded values of initial. After changing, we have done the mutation. We changed the bits. And now we will see what we get. We get some decoded value and the x value we are getting, and for each x value we are getting the function value. So now we see our function value is 1, this maximum here. And for the first one, that is the we have got the optimal solution, that is for this bit, when x is equals to 0.51, we are getting the best fitness, and this best fitness is what is showing that this solution is the optimal solution. You can also see from the graph of sine. So this is a sine curve, right? It goes from 0 to, this is 0, this is 1, it is at 0.5, this is the maximum. So at 0.5 you will always have the maximum when we are talking about the sine curve. So this is from graphicals, and we are also getting it from genetic algorithm. So for this simple kind of problems, we are not using genetic algorithm. We are using it for more complicated problems. But this is just an example, like how we proceed for solving a problem. This is the procedure for doing a problem using genetic algorithm. Now we saw like what is the procedure. This is using binary coded GA. Now there are some disadvantages of binary coded GA. So because of that, there is something we have to move on, that is called the real coded GA. Okay. So what are the disadvantages of binary coded GA? So first thing is obviously more computation. If we want more accuracy, if the length of string is very long, if you have a high population size, in that case we will have a very uh, complicated computation, and computation will take a lot of time. The second thing is lower accuracy. Yes, why lower accuracy? Because here you see when we are taking suppose small population size, we are getting searching only discrete part of the search space. We are not searching continuously. So there might be some way, some points where it might be missing the solution in some cases. So because of that, we are like skipping the main optimal solution, and we might be searching in and around that solution. So that is one thing, that accuracy is not that good in case of binary coded GA. Sometimes when we are dealing with complicated problems. Obviously, third is a longer computation for higher precision. Obviously, I discussed, and this is something called solution space discontinuity. Now this is again discussed in class. So what we have done, suppose if we have I discussed, this is the precision, that is what I denote by the precision, x to the power x xu minus xl by 2 to the power l minus 1. Now suppose if we keep precision as 1, in that case, and we take 2 bits, so what we'll have, we will have 0 1 1 0 0 1. This is 4 permutations, and based on that we will have 1 0 1 2 3, these 4 decoded values. But there might be a case where the optimal solution is at zero point 0.5. So if a optimal solution is zero point 0.5, then we are no way we are getting to that value, right? So we are skipping this point in the solution space. So to deal with such problems, we have to move to something called real coded GA. And okay, called space solution space discontinuity, like we are not searching continuously in the solution space. And lastly, there is called the Hamming cliff. uh, there is there is a term called Hamming distance, and how it is defined, it is defined by bit uh, one second. Hamming distance is defined as bit to bit difference from the two solutions or two population samples. So from here, if we take first bit, the difference between each of the bit, we will get this. For first bit 1, second bit also 1, third bit 1, and fourth bit also 1. So our Hamming distance is 4. But actually, if we are actual distance is what? If we decode it to get a decoded value, our decoded value is 8 for this, and for this one, our decoded value is 7, and the actual distance between the two solutions is 1. So our Hamming distance and actual distance are not similar. So when this is the problem, what happens is like when we're doing crossover or doing mutation, so we have to change more than one bit to get nearby solution. So this is the problem when the Hamming distance and actual distance are not, we are very far apart. So in general, what happens, like if you're changing only one bit or changing it crossover is at one side, we will get a solution nearby. but if the Hamming distance is very far, like very different from the actual distance, in that case we will need to do the crossover at more than one side. So this is also one problem that arises when we are doing is binary coded GA for very long strings or very long like high precision problems. So to get to arrive at better solutions, so there is the linear. This is the real coded GA. So in real coded GA, the thing is that the initial procedures will be kept same. This selection procedure will be same. The crossover and mutation will be approaching some new methods for solving the for doing this crossover and mutation. Now there are I will discussing these are already discussed in class, so I am not going too much into detail of this. So first is the linear crossover in real coded GA. If there are two parents, one parent is denoted by x1 to xn. This is a chromosome for first one, x1 to xn, and the chromosome for second one, yn to ym, and all are real values. Now we do a linear crossover. What we do? We'll select a single gene K at random from we select one gene at random from both the chromosomes, and then the children, the after crossover children are created in this manner. From x1 to xk minus 1, all the bits will be same. From xk plus 1 to xn, all everything will be same. For the xk value, we'll change it like 0.5 into yk plus 0.5 into xk. Okay, this is one solution. Then second solution after crossover is from again till k minus 1, and from k plus 1 it will be same, and for the kth bit, the kth gene will be changing 1.5 yk minus 0.5 xk. And thirdly, the third solution is this one, minus 0.5 yk plus 1.5 xk. So in this way we will be so when you're doing the crossover in this manner, what we do, we are searching like uh, in a finer resolution into the search space. That is, if there initially in that solution space discontinuity discuss that if the solution is at zero point 0.5, then we won't be able to get to such solution. But if we are proceeding in this manner, even if suppose we are values are in like 0.0, 1, 2, and like that, even if we have solutions at 0.5 or 1.5, we will be able to get at such solutions in this kind of crossover. Okay, so this is one first method. It is called linear crossover. Then there is a second method. This is called the simple arithmetic crossover. What we do, uh, again, this is similar to the binary crossover only, but the thing is that after we'll select one site on randomly, and what we'll do, multiply that site, multiply the value of that site by this form. This, yeah, alpha yk plus 1 minus alpha of xk. So we'll select alpha at random. Alpha will be something from 0 to 1. We'll select alpha from in this range randomly based on our requirement, and then from suppose from this bit onwards we'll be multiplying by this, like alpha into, suppose for this one will be alpha into 0.8 plus 1 minus alpha into point. So this 0.8 and 0.2 are coming from here and here, and then we'll get this one. Okay, so understood. So similarly for the second string also we'll do the same procedure. So this can be done for the entire string. This can be done for only one bit, that is for one bit also, and for part of the string. So this is a simple arithmetic operator. Based on our requirement, we will be following one of these, like following for the entire string or part of the string or only one bit in the string. And there is one more method of crossover that was developed by Kalyanmoy Dev from IIT Kanpur. He developed it in 1995. So what he did, he like the similar procedure. After from that, and if you have the initial solution, then we will be multiplying it instead of alpha and 1 minus alpha. It will be 0.5 into 1 plus beta into xi plus 1 minus beta into xi2. That is xi2 is the yi. So here it is denoting the variables by xi1 and xi2. We can also denote it by xi and yi. So it will be 1 plus beta into xi plus 1 minus beta into again yi in multiplied by 0.5. And similarly for the second part. And now how do we define beta? The beta is defined by this formula. So beta is 2 ui into to the power 1 by nc plus 1. Now what is ui? Ui is the randomly generated number. So a random number can be generated. I will show you in like a next lecture. I think will be doing some coding. We'll be solving a general this GA problem using coding. The thing is that one method of generating a random number in code is like, suppose you take one value from 0 to 1, we randomly pick. And how do we pick it? We can define pick it by using a uniform distribution. A uniform distribution is what? It is a distribution from 0 to 1 and the value is 1. So from this distribution we will randomly pick one value, and from this value we will do the inverse CDF of this value. And this inverse CDF can be done using normal or gamma or any distribution that we want. So the detailed procedure I will be seeing in like for when we'll do the coding. So this is one way of generating a random number. Okay, so we generate a random number ui, and then and eta c is the parameter that controls the crossover process. So this is a parameter that we define for based on our problem. A high value of the parameter will create a near parent solution. Remember this. When eta c is high, so if eta c is high, 1 by eta c will be low. So 2 ui to the power 1 by eta c will be low. So beta value will be small. If beta is small, then this 1 plus beta and 1 minus beta will be close to 1, and so the solution will be nearby xi and xi2. So we will be not having too much variation in the solution. We will be searching locally. It is near the initial solution only. But if the beta value is like eta value is low, in that case we will have high beta, and then we are searching for like slightly away from the local that is the initial solutions. Remember this. This is important. How do it? What is the significance of this parameter eta? Okay, so these were some methods for the new methods of crossover. Then some there you will see some methods for mutation. In mutation, what we do is change the bit, right? So what we do, a new bit is defined as this one, ui into xi. We will be changing the bit based on this formula. Yi is equal to ui into xu minus xl. So again, ui is the randomly generated number from between 0 and 1. So the new bit will be defined as xi, the initial bit that we had, plus ui minus 0.5 into delta. So we'll be getting ui randomly from 0 to 1. We can generate based on that uniform distribution. And after that, delta is the user defined maximum perturbation. Suppose this is xi, this point is delta I by 2, this is minus delta I by 2. So if ui is equals to 1, we'll get the solution, get a new mutated bit at 0.5 delta I. And if ui is equals to 0, we'll get the solution at minus 0.5 delta I. Because you can see it from the formula only. So this is how we do the random mutation, one way of doing the random mutation. And secondly, there is another method called the normally distributed mutation. Here what we do, how do we change the value of the bit? So if we have the bit value at xi, so we will be adding a n0 comma sigma I. That is, what is this? This is a normal distribution. Normal distribution is the mean n0 sigma means the mean is 0 and the standard deviation is sigma. So this is the normal distribution. This is the mean of a normal distribution, and the sigma is defined as sigma. Okay, so this is a 0 comma sigma normal distribution. So from this normal distribution we generate one number. Suppose based on this probability we have generated a number, and this number will be used here. That is, we substitute here, and then we'll get a new mutated bit, new mutated value for the bit which corresponding to xi. Okay. So now thing is that this will be dependent on sigma. A very high value of sigma means sigma, suppose high value of sigma means the solution is far away, the new solution will be very far away from the previous solution, and the low value of sigma means the new solution will be nearby to the previous solution. So based on the sigma of the normal distribution, we will have very our search space will be varying in that way. And lastly, there is a polynomial mutation. This was again given by Koildan Dev in one of his research papers. He defined as a new mutated string bit as xi plus delta I into xu minus xl. Xu minus xl is fixed. How is delta I defined? Delta I is again defined in the previous way that we defined crossover, that this one say a simple simulated binary crossover. So we do ui is same, then the power will be 1 by eta m minus eta m plus 1 minus 1 for if ui is less than 0.5. If ui is greater than 0.5, then we will be following this formula. So this was based on a lot of research and lot of simulations he has done. That it is not like he has just randomly given some formula. He has done a lot of simulations on different problems, and after in computer code, and after doing a lot of simulations, he arrived at this formula. So this is a comprehensive research problem. If you are interested later, you can like read his paper or his book, and then you can get a better idea of this. Okay, so this was about like real coded GA, and now what is the requirement of real coded GA? We have to do a solver multimodal optimization. What is multimodal? Like thing is it when there are like solution is not convex, there is more than one optima. In that case, what happens if we are doing simply GA? Then we will always arrive at the global optima. But sometimes we might be needing the this optima also. We might be needing. It's not always want a global optima. We sometimes are required. Okay, I don't want a global optima. I want the optima value that is like next to the global optima, based on our some requirement. So in that case, we have to slightly modify our procedure. So what happens when we are doing generic algorithm? Our the best solutions will be crowded near the this global optima. So this is called the overcrowded solution. So what we will do, we will try to make this solution slightly undercrowded so that some of the solutions also move to this optima. And how do we do that? There is something called sharing function. We will find, suppose we have when you're initializing, when you're doing the population, in doing the selection and then this crossover mutation, we will have some values here or some values here and there. Okay, we'll have some values. We'll be discarding those values, but we won't for this in this method we won't be discarding those values. What we will do, we'll find a distance between the solutions, distance between different solutions, and based on this suppose distance between the solutions, we will be getting defining a function called a sharing function. This is defined as 1 minus dij by sigma. Now sigma is defined again manually based on our problem, how type of problem we are solving, what is the range of the function, and based on these factors we are defining sigma. Don't confuse see this sigma with the standard deviation. No, this is not a standard deviation. This is a parameter that is defined manually based on our problem. And so we'll be doing, so if dij is less than sigma, we'll have this formula for sh dij, and if dij is greater than sigma, we'll replace it by 0. Now after that, we'll define a quantity called n nis count. This nis count will be defined as summation of the sharing function for each chromosome, and then after getting the nis count, we will be getting the modified fitness, the initial fitness divided by the nis count, and we will get them after getting the modified fitness. We will get some values here and there also in the like lower optimal solutions also. So we will solve one problem, and then we can see like what is the procedure for doing this. I think sir has already shown in the lecture video that how he solved one problem. Still, we'll see through some problems. Okay. Any doubts in the concept? Anything before we proceed to the problems? If you have, you can ask.
By selecting the crossover and mutation, we can select randomly any points, sir, in that field.
Um, for
Crossover and mutation, we are selecting some points, no, sir.
yeah, that site is you can select randomly. Yeah, that is true.
Okay.
The site is always selected randomly, but how we mutate or how we do the crossover, that is still there are different procedures for doing
Okay.
that. The site is
Okay.
always selected randomly. Yeah.
Okay.
Okay. So let us solve some conceptual problems first, then we'll solve the numerical. So first question is, if the niche count is large, then the solution is a crowded solution. Yeah, this is true. If the niche count is large, we'll have a crowded solution. It means the sharing function values are large and all the functions are nearby to each other. So in that case, we are saying that this is a crowded solution. True. Disadvantage of binary coded generic algorithms. Oh, yeah, one thing is more competition. Second, solution space discontinuity. I discussed already, and also lower accuracy. So all of the above. The standard genetic algorithms have the following steps. So we have to order the steps in the For first is first step is to to select the initial population. Second, we have to assign a fitness function. Assign the fitness function. After getting the fitness, we will do the perform algorithm. That is, we will put some solutions that are very good, has very good fitness, and then we'll keep those solutions. That is called elitism. And after elitism, we'll do the selection, is in tournament selection or proportional selection, like based on we can choose any of those methods. Perform selection. After that comes mutation, and lastly crossover, and at last comes mutation. So if we get, so it will be this, I think one choose initial, then fourth is assign fitness function, then elitism, selection, crossover, mutation. I think 1 4 2 3 5 6. This is the procedure of like doing a simple standard genetic algorithm problem. Okay, in case of a simulated binary crossover, a high value of the parameter will create respective child away from the parent solution. No, this is false. I already discussed here how the parameter value will be creating a solution. A high value of parameter value will be creating a near parent solution. I discussed it already. So this problem question is based on that. So the high value of parameter will create a solution near to the parent solution. Okay, so this is false. Okay, so we have a problem. Let us solve it. So there are three. It's a three variable problem. So x value ranges from -5 to 10, y value ranges from 0.001 to 0.005, and z value ranges from 10 to the power 3 to 10 to the power 4. So what should be the minimum length, string length at any point xyz coded in a binary string to achieve the two significant digit accuracy? So two significant digit accuracy, that is this pi value will be 0.01, that is 10 to the power -2. So if pi is 0.01, so we have to we have to achieve pi equal to 0.01 for all the three variables. So we'll be doing it for all the values x, y, z. For x, it will be 0.01 equal to x u minus xl by 2 to the power l minus 1. Now what is xu? Xu is 10, xl is -5, so plus 5, 2 to the power l minus 1. So we will get 2 to the power equals to 1 plus 15 by 0.01. Now if we solve, this is pi is denoted as a precision. It is not that pi equal 3.14. This is a symbol for precision. So yeah, we for simplicity we'll denote as p. Okay, this is the precision. This value that I discussed here. I think initially. Yeah, this xu minus xl by 2 to the power l minus 1 is comes from this formula. Okay, so this part is called the precision or accuracy, and this is denoted by pi. It is not and this is not pi equal to 3.14, and it is given zero point 0, and this is given in the question 10 to the power minus 2. 10 to the power minus 2 is 0.01. That's right. uh, so we'll solve this problem. So I think what's 1 plus 15 by this is something I think 2 to the power. And this will be approximately 10. I think it is this 2 to the power 10 plus something, so it will be approx 2 to the power 10. L will be approximately 10 here. Okay, so 2 to the power 10 is 1024. 1024 plus something is 1501, and 2 to the power 11 is I think 2048. Yeah, so it will be L is approximately 10 here. Now for the second, that is for y, we'll do it for again y. 0.01 we have to go under accuracy yu minus yl 2 to the power l minus 1. What is yu? Upper limit is 0.005, lower limit is 0.001. So 2 to the power l is equals to 1 plus so I think this will be 0.4 0.401.4, and this will approximately come as l is equal to 0.48, which is approximately equal to 0. So l will be 0 for this, for the second one, and for the third one z 0.01. The ZU minus ZL, ZU is 10 to the power 4 minus 10 to the power 3 by 2 to the power L minus 1. So 2 to the power L is equals to 1 plus 9000 by 0.01, right? So equal to 900,001. L will be approximately, I think this, if you take log on both sides, it will be this one. log of 900,001 log of 2 is equals to approximately 19.7. This will be equals to 20. Okay, this is sorry. This will be 11. If we again do it by the same, L is equal to log of 1 by log of 2, it will be around 10.55. So we'll take it as 11. And for this also, this is if we, the thing is that we shouldn't give 0 bit, because if we give 0 bit, then there is no significance of the value of 1. So we will be, the least integer we can give is 1. So we will be converting it this 0.48 to 1 only here. So 1 bit for y, 20 bits for z, and 11 bits for x. So the final chromosome will be, for x it will be 11, for x, for y it will be 1, and for z it will be 20. So it is equal to 32 is the total bit size of the chromosome. So it is 32. Okay. So get to this two significant digit accuracy, we will have to get minimum coded length of 32. Okay, I hope this is clear. Let's move to the next problem. So this is a slightly lengthy problem. We'll solve this problem now. Now consider the function f(x) equal to x square equal f(x) equal to x square plus x of into cos of x. The maximum value of the function are to be determined. The upper and lower bound of x is 10 and minus 10. Initial binary population is given. Okay. So initial binary population is given. So we'll do the procedure, do the solution. Okay. One, 6 solutions are given. The binary solutions are 1 1 0 1 0 0 1 0 1 1 0 0 0 1 1 1 0 1 0 0 1 0 1 1 1 1 0 0 0 0 1 0 1 1 1 0. This is a binary solution. Now first we have to get the decoded value. Now the decoded value is, I taught you how do we get decoded value? It is 0 into 2 to the power 0 plus 0 into 2 to the power 1, like that. So for this one it will be 2 to the power 2, that is 4, 4 plus 3, 4 plus 16 plus 32. Okay. For the second one again, 4 plus 8 plus 32. For third one, 1 plus 4 plus 8 plus 16. Okay. So for the terms that have 0, we are not multiplying it by that power. I hope this is clear. Okay, this is this decoding I have taught in the previous class also. For this one, for first time it will be 1, for the second time it will be 2, and for the fourth term it will be 8, right? 2 to the power 3 will be 8, and for this one it will be 16 plus 32, this 2 to the power 4 plus 2 to the power 5, and for this one 2 plus 4 plus 8 plus 32. So we'll have the decoded values, 32 plus 16 plus 4, 52. For this it will be 44, this will be 29, this will be 11, this will be 48, and the last one I think 46, correct? If I make any calculation mistake, just let me know, okay? So we have a decoded value. Now we have to find the xi value. How is the xi defined? Xi is equal to xi mean. Xi mean is how much here? This the xi mean is minus 10 xiu oblique xi max is equal to plus 10. Okay, so xi will be minus 10 plus xu is equal to 10 minus minus plus 10 plus 10 divided by 2 divided by L. What is L here? L will be 6 because there is a 6-bit string. 2 to the power 6 minus 1 into decoded value. It will be minus 10 plus 20 by 63 into D. Now for each of this we will be getting the value of xi. So for each decoded value, if we substitute, we will get the xi as 6.5. Then for the second one, it will be 3.96. For the third one, minus 10 plus minus 0.79. Then the next one is minus 6.5. 5.23, and for the last one 4.6. So we got the exercise. Now we will get the fitness value. How do we define the fitness? Fitness is a substituting xi in this formula. X square plus x into cos of x. So we will substitute this xi value in that in this formula. So let us do that. 6.5 whole square plus in first one will come 48.4. For similarly 19.59. The second one, for the third one again minus 0.79. minus 0.16. Just let me know, okay, if I do any calculation mistake. So if you substitute minus 6.5. 35.5. And the last one, I think 25. So this is the fitness values, okay. So you can see this is the highest fitness and followed by the, and this is the lowest fitness. So what we will do, our solution will be mostly, even if we do the crossover, our solution will be this is crowded near this solution. So what we do, we have to do the modified fitness. And how do we modify? This is the procedure that I decide. We will use a sharing function. First find a distance matrix. From that we will get the sharing function. Then we will get a niche count, and finally the modified fitness. Okay. So now first we will get the distance matrix. So we will denote its solution by this. Suppose 6.5, 3.96, 79 minus 6.5. Again here 6.5. And dij is a di minus dj. We will take the absolute, okay. We are taking a distance is always positive, so even if it is minus, we will be taking the absolute value only. 6.5, 6.5 is 0. uh, 6.5 and 3.96 is 2.54. 6.5 and minus 0.79 is 7.29. Then we have 13. This is 1.27, and lastly 1.9. Okay. Now again 3.96 and 6.5, it is same 2.54. This is 0. 3.96 and 0.79, 4.75. Then we have 10.46. Then 1.27, and lastly 0.64. Now next, these two values will be same. That is as 0.79 and 6.5. This is same 7.29. This is 4.75. This is 0. Then next is, it will be 5.7, 6.02, and lastly 5.39. For this, these three will be coming here: 13, 10.46, 0, 7.3, and 11.1. For 5.23, again 1.27, 1.27, 6.02, 11.73, 0, and 0.63. And lastly 1.9, 0.64, 5.39, 11.1, 0.63, and 0. Okay, it's the distance matrix that we got. Now we have to do the find the sharing function equal to 1 minus dij by sigma if dij is less than sigma. Now what is the sigma value given here? They have given sigma equals to 5. This is user defined. So and 0 if dij is greater than sigma which is equals to 5. So if dij is greater than 5, we will be replacing that as sharing function value as 0. If it is less than 5, we will be putting some value. Sharing function means like if it is closed, then it will have a high value of sharing function. That is the definition of sharing. Like if the solutions are close by, then the sharing it will have like high value of sharing function, and if the solutions are far, the sharing function value will be low. So let's construct the matrix. So this is our solution 1, 2, 3, 4, 6, and lastly we'll get the least count. Okay. So for the first one, you can see it is 0. If distance is 0, 1 minus 0 is 1. For the second one, if 2.54 is less than 5, so we'll have a sharing function value. So the sharing function value will be 0.49. So from this formula. For the third one, the value is 7.29. It is greater than 5, so it will be 0. For the fourth one, again 13 greater than 5, so 0. Then it is 1.27, so it will use by the calculate by the formula, and the value will come as 0.74. And for the sixth one, it will be 0.62. Similarly, we can get for other
So
matrices.
can you repeat once again, sir, this step?
Yeah, so this value is coming from the distance, suppose. So how 0.49 is coming? It is for this corresponding this element. What is the value? Dij is 2.54, right? And 2 point we have saying that when dij is less than sigma, we will be using this formula 1 minus dij by sigma, and sigma is given as 5. So here 2.54 is less than 5, so we'll be calculating this 1 minus 2.54 by 5 will be coming as 0.49.
Okay, sir.
And here you can see it is 7.29. This is greater than 5. If it is greater than the sigma, then we'll be replacing by 0. So that's why it is 0 here. Okay. Okay. Similarly, for the second one, you can see these two elements are similar. This is a transpose. This one, a symmetric matrix, right? So these two values are similar. This and these are similar. So what is similar elements? The values will be similar only. So we need not calculate again and again. Okay. For the second row, this is again. Now third element is 4.75. For 4.75, we will have the S is equal to 0.05. Then again for 10.46, we will have 0. For 1.27, we will have 0.74, and for 0.64, we will have 0.87. Okay. Again for the third row now. So this will be 0, this will be 0.05, this will be 1. So the third next three elements are what? 5.7, 6.02, and 5.39. All the three values are greater than 5, so everything, all the values will be 0. Now for the fourth row, that is when there is 13, so it will be 0, 0, 0. This is the 13 is 0, 10.460, again 5.70. So this it will be 1, 11.73 is 0, 11.1 is 0. Now next for the fifth row, again 1.27. For that we already calculated 0.74, 0.74. Now for 6.02 it will be 0, 11.73 is 0, 1 for 0, and 0.06.63 we will have 0.87. For the sixth row, again we will have 0.62 coming from this way, 0.87, 0, 0, 0.87, and lastly 1. So niche count will be what? Summation of the values in rows. We have to sum up these values for each row and we'll get the niche count. So for the first row, the niche count is how much? 1 plus 0.49 plus 0.74 plus 0.62, becoming as 2.85. For the second, 1 plus 0.49 plus 0.05 plus 0.74 plus 0.87. For the second third row, 1.05. For the fourth row, it is 1 and 0.74 plus 0.74. For the last one, 0.62. So we have the niche count. So now we have the modified fitness. How do we get the modified fitness? It will be F by NC. So the values will be, we already have F. F values are what? This one, I think we had this. 48.4, 19.59. I'll just write the values here. 0.59. Third value is minus 0.16. Fourth value is 35.5, 32.4. And the last value is 25.6. We'll divide it by the niche count for corresponding row. So yeah, 48.4 divided by 2.8. This is 16.98. 19.59 divided by minus 0.16 divided by 1.05. Now see, this minus 0.16 and 35.5, these are the least crowded solutions. So that's why the niche value is 1 for these solutions. Okay, that is less. And this is the most crowded solution, 3.36. This is coming to 25.63. 0.4 divided by 7, and lastly 7.61. I think we'll have there is some mistake or what? This value is fine, approx 30, this is approx 16.9. 6.2 is coming fine. So yeah. 4.8 and minus 0.83. I think there is some calculation mistake. Maybe okay, there is some mistake in calculation of these values. Okay. Actually, I took the this cos of x. I have taken in x value. I have taken in degree. So the thing is that I have to take in radian. So in the scientific calculator, I have put these values as degrees. So I have to take in radian. So let's recalculate this f values based on radian. Okay. I think this value is coming as 16.1. Or let's calculate for each of these. Cos of 6.5 into 47.6. Next, we will do it for 3.96. 13.4. X square plus x D divided by 63 into 0.11, it is coming, I think. Cos of for 4.6 minus 2.88. So these are the modified values. I think there is some mistake in the third value in the solution maybe. So yeah, let us write the modified table. Okay, for the what are the fitness values again? 47.6 minus 13.4, 1, 34.9, 16.1, and my last one is minus 2.88. Value is correctly at 0, 1, 1, 1, 0, 1. So this is 1. 1 into 2 square 4, 1 into 2 cube 8, plus 1 into 16. Fine. Minus 0.79. Okay. So the modified fitness we will divide it by the niche count. So for the first one is only 47.6 divided by 2.85. So it's coming as 16.7. Second one is minus 13.4 divided by 3.15 minus 4.25. For the third one is uh, minus 0.11 divided by 1.05 b minus 0 1. Third one for the fourth one 34.9 divided by 1 is approximately 34.9 only. Then 16.1 divided by 3.35 4.8, and the last one is minus 2.88 divided by 3.36 minus 0.85. So these are the modified fitness values. So let us check the solutions. One is minus is 16.7, yeah, approximately 16.7. Second is minus 4.2 given here, yeah, minus 4.2. The third value is different here. The third value we are not sure. I think there's a mistake in the question. Fourth value is 34.9. This is fine. Then the fifth value is 4.8. It is fine. 4.8 is fine. Last is minus 0.83. It is fine. I have shown the solution. Just if you have time, you just repeat the solution once. I might have done some mistake calculation. I don't know, but I don't think I have done any mistake. But there might be a mistake, typing mistake in the solution only for the
So
third one.
we have to consider in radians, sir.
What? I didn't understand.
No, the X value we have to consider in radians, not in degree.
Yeah, radian. Yeah, we have to consider radian only. When I'm considering degree, the thing is that we are not getting into the solution. So the x values are in radian only here. Remember that I think in whatever problem comes in the exam also, it will be this, if there are cos x and sin x, these values, x values will be radian only. So when you're calculating using scientific calculator, you have to put the value in radian. Like there is an option for keeping it a radian or degree, just mention as radian. Okay. So it is not degree, it is radian. Okay. There is some mistake in the third, this one third, there is some typing mistake, I think. So yeah. So this is based on the, for the same problem only. The thing is that here sigma is equals to 30. So what will happen when sigma? I won't be solving this problem again. It will procedure go with the same procedure only. The thing is that when you're giving sigma equals to 30 here, you can see all the values are less than 30. So there will be no zeros here. So everything will have a as a sharing function value. When all the values will have sharing function, so we'll get a different niche count. All values will have a so different niche count. Okay. So now based on that niche count, you will have a modified fitness. If you want, I can solve it, but again, the same procedure only. So that's why I'm not wanting like it's like same going through some arithmetic calculations only, nothing else. Yeah, and function is bit different. This function will be different. Otherwise, the whole procedure is same. Since the bits are same, the procedure will be same. The thing is that the function of when you calculate the fitness function, in place of cos x, we have to this cos of. I think there is a mistake. This is cos of x. Okay, it is cos of x plus x to the power sin x, not cos. Okay, there is some typing mistake here, so just be careful. Just solve this problem on your own. If you have any face any problem, just ask me in the next class. Okay. As remember, this is not cos. This is cos of x plus x to the power sin x, and x is in radian. So convert the x values to radian, and then just solve this problem. Everything is same. A distance matrix will be same. No, distance matrix will be different because x is 0 to 100, so it will be slightly different. But again, the same procedure. Okay, let's proceed to some next some different kind of problems. Okay, suppose a GA uses chromosomes of the form X equals to A, B, C, D, E, F, G, H with a fixed length of 8 genes. Each gene can be any digit between 0 to 9. Each gene can be digit between 0 to 9. Let the fitness of the individual of X be calculated. F E plus B minus of C plus D plus of E plus F minus of G plus. Okay. 1 second. Just a minute. I'll drink some water. Okay. So now let the initial population. The initial population is given as x1, x2, x3, x4. 4, 1, 3, 5, 2. X2 is 8, 7, 1, 2, 6, 6, 0, 1. X3 is 2392128 and x4 is okay. So evaluate the fitness of each of the individual, arrange them in order of the fittest first and least fit at the last. Okay, so how do we evaluate the fitness? It's like same a plus b. So let us do this 6 plus 5 minus of 4 plus 1 plus of 3 plus 5 minus of 3 plus 2 equals to 11 minus 19 minus 10 is equals to 9. So 4 same here. 8 plus 7 15 minus 3 plus 12 minus 1 equals to 27 minus 4 is 23. For this one 2 plus 3 5 11 plus 3 5 plus 3 8 8 minus 14 8 minus 24 is minus 16, and for the last one is 5 minus 13 plus 2 minus 13. 7 minus 26 is minus 19. So arranging order of fitness, I think x2 is the highest most fit, then comes x1, then x3, then x4. x2 x1 x3. So I think first solution. Okay, simple problem. Okay, next question, cross the fittest two individuals using 1 point crossover at the middle point. Okay, so fittest two individuals are what? X2 and x1. So we have to cross over this. So the individuals are, let me just write parent 6541 3532 32, and second one is 8712 6601. So these are the parent. What is it? To do the crossover at the middle point. This is the crossover side. After crossover, what we'll get? 6541 6601, and here 8712 3532. So 8712 3532 and 6541 6601. I think option A. Yeah. So this is the child. Okay, this is simple crossover. Okay. Now this is one part of solution. The second is cross the second and the third fittest individuals using the 2 point crossover. That is points B and F. Okay, the second fittest is the this one. X1 is second fittest, and the third fittest is the X3. So let us write these solutions. 6541 3532 6541 and the other one is 2392 1285. Okay, so what we have to do, we have to cross over at two sides. So what are two sides? B and F. Let us see what is F. F is the third from the last, and B is the second from the first. So one crossover side will be this one, third from the last, and the other crossover side will be this one. So the child. So first thing will be same 5. Then this will be 921 will be coming here, and 285 will be 285 will be sorry, be the third, the point will be not this one, it will be it's, the point will be this crossover side, it will be B and F. It is mentioned that after F is this one, after B is this one. So when it is mentioned the particular side, it means that after that point. Okay, this is this is B and this is F. So after B and after F. Okay, so it will be 65921 and 85 will be coming. So the last side will be coming second. So it is changing only this part of the string. 2 3 4 1 3 5 and last is 8 5. So we are taking two crossover sides. It is the whatever portion that comes in between the two crossover sides will be changing that. So this is the solution 65921 and 32 and 2 3 4 1 3 5 and 8 5. So next, across the first and the third series individuals using single point crossover, select the correct answer. So between points C and D. Okay, let's see. So what the first and the third? First is x2 and third is x3. 87126601. First one, and the second one is the third fittest is the 2392 1285. We have to select the crossover side at where between C and D. A, B, C and D. So this is the crossover side. This is C, this is D. Between C and D, this is the crossover side. So it will be 871212285 and 2392660. Okay, these are the children. Okay, so we obtain six set of new solutions, new child. So our next problem will be based on that. So the new population consists of the six offspring individuals and received a crossover operation in the above. Evaluate the fitness of the new population. Select the correct order of fitness. Okay, so we have the population. So let us write the population first. First one is which one? Yeah. 8712 Second offspring, then a third offspring is on this one 6592 1232 6592, and the last one is 2341 3585. And for the last crossover we have this one 8712 1285 5, and the last one is 23926601. So now calculate the fitness. Fitness is a plus b minus c plus a. So it is like 8 plus 7, 15, minus of 3 plus 3 plus 8, 5 is 8, minus of 3 plus 2, 5. 15 plus 8, 23 minus 8, 15. 11 minus 5 plus 12 minus 1, 23 minus 6 plus 17. 11 minus 11 plus 3 minus 5 minus 2. Next is 5 minus 5 plus 8. Which step? This fitness function calculation. This step, it is like simple, like we have seen now. F is equals to a plus b minus of c plus d plus e plus f minus of g plus h. And what are, this is a, this is b, this is c, this is d, this is e, this is f, this is g. So these are the bits now for the solution. So it is a plus b minus of c plus d plus e plus f minus of g plus h. So it is just doing these calculations. 8 minus 13 is equal to minus 5. So here 8 plus 7 is 15 minus 3 plus 3. 5 minus 11 plus 11. So the highest fit is 17, then O2 greater than O1, then O6, O5, O3, and O4. As the overall fitness improves, so we are getting 3 fit solutions. Overall fitness is 17 plus 15. If we do the summation, 17 plus 15 plus 4 plus 2 minus of 7. So it will be uh, 21, 21 plus 17, 38. 38 minus 7 is 31. This is the total fitness after crossover. And before crossover, the total fitness was, I think, 23 plus 9 minus 16 minus 19. So it was very less. It is something in negative. Equal to minus 6. So yeah, overall fitness has improved. So this is yes. The last question. By looking at the fitness function and considering the genes can only be digits in 0 and 9, find the chromosomes representing the optima. So the fitness function is given as what? F is equals to a plus b minus of c plus d plus of e plus f minus of g plus h. So the thing is that we have to maximize the fitness function. If we have to maximize, then which these values should be minimum, since this is minus, and this 2 should be maximum since this is positive. So a plus a and b will get 9, 9. We can take any value between 0 and 9. So we'll put a maximum value of 9 and 9 in a and b and e and f. And we'll put zeros in c, d and g, h. So if we put this string together, it is 990, 9900. This is the optimal solution. And at x optimal, the maximum fitness, again fitness is what? 9 plus 9, 4 into 9 is equal to 36. There is, so the negative term is 0. So it is 36. Okay. I hope this is clear. If there are any doubts, you can ask me. It is this one, no? A plus B, 9 plus 9 plus 9 plus 9 minus 0 minus 0. So 4 into 9, 36. Any other doubts? Sai Krishna, you told that you had some doubt from the previous assignment, I think.
Yes, sir. Yes, sir.
Yeah, which one? That week 7 or week 6?
Week 7, sir. Question number 2 and 16, sir.
Okay, week 7. Question number 2.
Yes, sir.
If the parent solutions are 101011, that one, right?
Yes, sir. But correct answer is 011 011, sir. But the assignment it is given as 101 011. It is wrong, I think.
Which indicates one of the new offspring.
What is the answer, sir?
One, 1 second. Let me see.
Okay, sir.
101. Yeah, yeah, it is wrong. They have just given the answer like they've given the parent only, no, in the answer.
Yes, sir. But
Yeah, yeah, it will be 101 001 or else 011 011. Yeah, that is true. 011 011 is the correct answer. Yeah.
yes, sir.
So
Yeah,
yeah, you have to tell this to, I think, the faculty, or I will tell. Okay, I will just mail you that there is a
in
mistake.
the question number 16 also they have to give two copies, sir. But correct answer is three copies.
1 second.
Okay, sir.
Suppose you are applying tournament selection and use a tournament size of 3, then the best solution in the population pool will have, it should be 3 copies. Yeah,
Yes, sir. But answer is given as two copies, sir. Is
yeah,
it?
yeah, yeah. This is also a mistake.
I will mail to discussion forum, sir. No one can respond at that assignment release answers release day, sir.
Okay, okay. Just keep it in discussion forum, or also, yeah, you can drop a mail also to the
Send
professor.
me the mail ID, sir. Is there any mail ID? I will mail to discussion forum, sir. No one can respond till now.
1 second.
Please revise the assignment scores also. I will message them.
Okay, okay, okay. Actually, yeah, I will ask HODC for NOC common. Okay, the thing is that I cannot correct this, change the assignments. So this changing the assignment questions and this thing, this is in the hands of the professor and the NPTEL coordinator. Only they can change it. So I will just drop a mail to them. After
Okay,
that,
sir.
yeah, after that, they have to take a necessary step. Okay.
These two corrections are informed to your professor, sir.
Yeah, yeah, I will inform it to the professor. Okay.
Okay, okay, sir.
Okay. Yeah, yeah, you are correct. These options are wrong. Actually, the answers are wrong, given wrong.
Okay, sir. Okay.
Okay. Yeah. Anything else? Okay. If there are nothing else, then let us close today's session. Thank you for attending, and have a good evening. Bye.